Hello, hello, hello. I wanted to talk some about homogeneous differential equations, since I talked about linear differential equations and not exact, I haven't done exact yet, linear and Bernoulli differential equations. Homogeneous is a pretty common type, so let's talk about it. Remember before, when I had the differential equations, in the last video I started with this differential equation right here. And if you notice, this left side is, you could think of it as a multivariable function, f of x comma y, right? It's got an x and it's got a y. And in general, you'll see your differential equations with x and y's, all mixed up together. If you don't, you have a very lucky and very easy to solve differential equation. So if we think of the sides as multivariable functions of f of x and f of y, or as f of x comma y. In other words, you put in an x and you put in a y and you get an output. So what a homogeneous differential equation is it's a differential equation such that f of tx ty is t to the n times f of x y. T is and t and n are just constants in the real numbers, and we say it's homogeneous to the nth degree when we can pull out a factor of t to the n. So maybe an example of that would probably be nice. I don't know, dy over dx is is equal to x cubed plus x squared y. Okay, so we consider this part here to be f of x y, a multivariable function. If we plug in tx and ty, we get that that's tx cubed plus, and we could write it as t cubed because we have a t squared times a t cubed times x squared y, and that's t cubed times x cubed plus x squared y, which is just t cubed times f of x y. So this function here is homogeneous of degree 3. That's how you test for homogeneity. So what this is saying is, this is the test, but now we wanna, there's a nice substitution that we can use for homogeneous functions. Let's say I let t to be 1 over x, because then the 1 over x and the 1 over x and the x here would cancel. And let's see what that gives us. This would tell me that by the definition of homogeneity, if t is 1 over x, that means 1 over x to the n times f of x y is f of, I'll just for now write it as x over x, comma y over x, and x over x is just 1. So if this x variable is held constant at a 1, then there's really only one variable that can change, and so we could write f in terms of a single variable function. I'll call it phi of just y over x. And so then that would mean, if I multiply both sides by x to the n, that f of x y is equal to x to the n times phi of y over x. And this suggests the substitution in here, since we have this kind of nasty input of y over x, it would suggest, let's change that to just a singular input, and let's call that v. So we just have phi of v instead of phi of y over x. And multiply both sides by x, y is equal to vx. This is the substitution that you would want to use. You can use it for any homogeneous differential equation, and after some algebra, it will turn the differential equation into a separable differential equation, because if y is equal to vx, then f of x comma vx equals x to the n times phi of v. That is separable already. See, this is only in terms of x, so we could just divide by x to the n here, and then this is only in terms of v. So the whole side here is in terms of x, the whole side here is in terms of v, and so you can integrate both sides and get a solution to the differential equation. If instead I were to let t be equal to 1 over y, you would end up finding that I would make the substitution, I would want to make x over y be equal to v, or in other words, x being equal to vy. This isn't quite as common of a substitution, but sometimes sometimes it's useful in the differential equation. You can use either one, but sometimes one substitution just works out a little nicer than the other. So let me do an example. So let's say we have 6x squared minus 7y squared dx minus 14xy dy is equal to 0. This is a homogeneous differential equation. Really the easiest way to tell without using the fancy definition is just look at the exponents, all right? Do all the terms, when they multiply together, do their exponents all add up to 2, basically? This is a 2, this is a 2, this is a 1, and that's a 1, so when you add them together, you get a 2. So you could, if you plugged in the tx and the ty, you could just factor out a t squared. So this differential equation is homogeneous of degree 2. So let's just use, you can, if you're watching, you can try using x is equal to vy. If you do it right, you get the same answer as me. But I'm going to let y be equal to vx. I wrote xv, but normally you write vx. Y is equal to vx. That's the trick, so to say. And you got to remember, actually, yeah, it's good that I use this one. You got to remember the product rule here, because you have to write your differentials of y and your differentials of x in terms of only v and x. You can only have one independent and one dependent variable. So dy is v dx plus x dv. Just remember that. So 6x squared minus 7v squared x squared dx minus 14x squared v, because it's x times a vx. And now I'm going to just point out here that it was good that I used y equal vx and not x equals yv, because this coefficient here in front of the dy is a lot simpler than, well, not a lot simpler, but it's simpler than this coefficient here. So I know this dy is going to turn into something bigger. It's going to turn into v dx plus x dv. So if I only am multiplying by a monomial instead of by a binomial, it just makes computation a little easier. So in general, if the dy has the less complicated coefficient, go with y equals vx. If the dx has the less complicated coefficient, go with x equals vy. And you could, it doesn't matter which one you go with, it just makes it a little nicer to deal with. So v dx plus x dv. And that's equal to 0. So now it's really just algebra from this point. So 6x squared dx minus 7v cubed x squared dx. Hopefully I don't mess up on the algebra though. That's minus 14x squared v squared dx minus 14x cubed, yeah, v dv. That's equal to 0. So this is a dx, a dx, a dx, and that's a dv. Okay. That's how I always go about it anyways. So 6x squared, these are similar, so this is minus 21 v squared x squared dx, and that's equal to 14 x cubed v dv. Hopefully you can see that this is separable already, but oh, I forgot the dx here, dx. But let's mess around with it some. So I can factor out an x squared and a dx, so that's x squared times 6 minus 21v squared dx is equal to 14x cubed v dv. Now you really should be seeing it separable. So x squared over 14x cubed dx is v over 6 minus 21v squared dv. And I'm going to just write this as 1 over 14x dx is v over 6 minus 21v squared. So integrate both sides here. Integrate, that's a bad integral. Integrate. This is 1/14 natural log x. And this is equal to, now, this can be done, the second integral with u substitution. Let u be equal to 6 minus 21v squared. Du is negative 42v dv. So if I multiply by a negative 42 and then divide by a negative 42, then I have really just multiplied by 1, but I'm just making it work out nice. So however you want to do it, your antiderivative should be negative 1 over 42 natural log of 6 minus 21v squared plus c. And you could clean it up a bit by multiplying by a 40. You could multiply by 42. That's probably how you'd see it in a textbook. You'd see it in a textbook as, oh, well, we're not done yet. We have to, yeah. Well, let's do that first. Make it 3 natural log x is, let's make it 3 natural log x plus natural log of 6 minus 21v squared is c sub 1, where it's just a different constant, because 42 times a constant is still a constant. Whoa, okay. So we have this. Now we just have to replace v. We said y is equal to vx, so v is equal to y over x, and so we can just replace the v with the y over x, and we'd be done. So 3 natural log x plus natural log of 6 minus 21y squared over x squared is equal to c. They usually don't go to the trouble in most differential equation books, but you could see it written as natural log of x cubed plus 6 minus 21 y squared over x squared is equal to c. That's probably the most compact solution. And yeah, that's how you solve homogeneous differential equations. Once you recognize the homogeneity and you just substitute y equals vx, it's really just a bunch of algebra, and you can turn it into a separable differential equation.